Protons and neutrons are really important subatomic particles, but when it comes to a lot of what we think about as chemistry and chemical reactivity, that's really taking place amongst the electrons. So it's important for us to be able to figure out where those electrons live inside of an atom. So as we saw in previous chapters, electrons exist outside the nucleus in what we usually refer to as an electron cloud. But it's not just a random cloud. It's a series of very specific shells and subshells. So when we want to start putting, for lack of a better term, an address on all of these electrons, we need to designate those shells and subshells. So shells are given normal numbers. Subshells are usually designated as a type of orbital, S, P, D, or F. And those different types of orbitals have different shapes, have different behavior. It's probably not that important for us to get into a lot of detail on this in this class, but it's pretty fascinating to see how those different shapes can affect behavior both on the microscale and the macro scale. So this shorthand system that we've developed for designating these shells and subshells is what's called an electron configuration. When we look at an electron configuration, and we'll look at an example in a minute, electrons fill in this order. So we can break this down. Here are the S-type orbitals. Each shell only has one s orbital, and every orbital can hold 2 electrons. So in the first level, in shell number 1, there's only an s orbital. It can only hold 2 electrons. When we move to the second shell, that can have both s and p orbitals. P orbitals, there are 3 p orbitals. Each can hold 2 electrons, so the p orbitals can hold up to 6. So the second shell can hold 8, 6 electrons in the P, 2 more in the S. And it just keeps growing. You see we've got this sort of diagonal fill pattern as we go through. So looking at the periodic table, we can now get back to, remember we talked about this being the S block of the periodic table. Well, that's because the orbitals that are being filled, the subshells that are being filled here, are s orbitals. Similarly, we call this the p block. The p block is p orbitals being filled as the last electrons. Transition metals, the d block, d orbitals being filled. Rare earths, the f block, f orbitals being filled. So we can think about the periodic table broken down that way, and it really does help define the behavior of these elements. So here is an example of an electron configuration. Sodium atom has an electron configuration of 1s2, 2s2, 2p6, 3s2. In the first energy level, or in the first shell, there's an s orbital that can hold 2 electrons. In the second, number 2 here, there's an s that can hold 2 electrons and 3 p's that can hold 6 electrons. When we get up to sodium, we run out of electrons at the 3s, and there's just 1 there. The important thing to look at in these electron configurations is this distinction between the core electrons and the valence electrons, because the valence electrons are really what's defining everything that's going on. They're defining almost all of the chemistry of, in this case, sodium. The rest of these are, well, that's a noble gas number of electrons, right? That's the same electron configuration, that's the same number of electrons as neon has. So sometimes we abbreviate these, we abbreviate the core electrons using a noble gas designation, and then just put the valence electrons on at the end. So looking at this periodic table again, within each group, within each column of the periodic table, all of the elements have the same valence electron configuration, right? All of the alkali metals have a S1 valence electron configuration, whether it's 1s1, 2s1, 3s1, 4s1, 5s1. They all have the same valence electron configuration. Same thing, we can go over here. This is P4 for oxygen. Sulfur is a P4, selenium is a P4, tellurium is a P4, polonium P4, linolenium P4 as well, although they didn't include those down in this part of the figure in your book. We're going to be looking at a lot of information about electrons. Again, thinking about core versus valence electrons is important, and being able to work with some of those electron configurations is certainly useful as we move forward and start talking about chemistry and chemical reactivity specifically.